Hi students, now I am going to explain you one of the important topics of chemistry, that is coordination compounds. Okay? So, before I explain about the coordination compounds, you should know first of all what are coordination compounds. Okay? So, first of all you should know what are molecular or addition compounds. See, if a solution containing 2 or more stable salts in a stoichiometric ratio and such solution when evaporated, the result is formation of molecular or addition compound. Okay. Basically, there are two types of molecular or addition compounds. The first category is double salts. What are these? Okay. See, you take a beaker in which aqueous K2SO4 and aqueous aluminum sulphate are poured. Okay. Now, this solution is evaporated. Now, the result is the formation of a double salt. Okay. Now, what is the characteristic feature of the double salt? When this double salt is dissolved in water, you will get the test for potassium ion, you will get the test for aluminum ion, and also will get the test for sulphate ion. Okay. Here you can see some other examples like carnallite, okay, Morse salt and potash alum. The second category is coordination compounds. These are also prepared in the similar manner. Look at here, in a beaker, okay, aqueous AgCN and aqueous KCN are added. Okay. This solution is evaporated. Now, the result is the formation of complex compound or the coordination compound. Here you can have the test for potassium ion, that is, it will give the positive test for potassium ion, but for silver ion or cyanide ion you do not get the test, because they are involved in the formation of the complex ion. Okay. So, these are called as the coordination compounds. Okay. Next, we will have a comparison between double salts and coordination compounds. Okay. When double salt is dissolved in water, we will get the test for all the corresponding ions. So, here we will get the test for potassium ion, aluminum ion and sulphate ion. But when this coordination compound is dissolved in water, we will get the test for only potassium ion, but not for silver ion and also for not for the cyanide ion. Okay. See, the question will come like this: which of the following is a set of complex and double salt respectively? So, you have to identify a complex salt and a double salt. So, option 1, this is a simple salt, it is a complex. Okay. Option 2, both are coordination compounds, but in option 3, this is a coordination compound, but you know this is a double salt. So, option 3 is the right option. You can see this is a complex and this is also a complex compound. Now, before we understand about the coordination compounds, there is certain terminology which you have to understand. Okay. So, the important terms used in coordination chemistry. Coordination entity, it is a starting important term. Here coordination entity comprises of central metal atom or an ion to which fixed number of ions or molecules are bonded. Okay. Now, look at here, this is the coordination entity. Here central metal ion is there to which fixed number of ions or molecules are bonded. So, this is a coordination entity. Another example, metal and fixed number of molecules bonded. One more example, okay, and these are the coordination entities. Okay. The next important term is central atom or ion. Okay. So, in the coordination entity, to the central atom or ion, ligands are bound. The ligands can be molecules or ions. Okay. Now, you see this complex, it is a cobalt complex in which cobalt 3 plus ion is the central metal ion. Okay. This is a nickel complex in which nickel atom is the central metal atom, and you can see here, and the third one is this iron complex in which Fe2 plus is the central metal ion. These are electron deficient species, therefore, function as Lewis acids. Central atom or ion. See, in a coordination entity, whatever you have seen just now, this in the coordination entity, the metal atom or ion to which fixed number of molecules or ions are bound in a definite geometrical arrangement, that particular atom or ion is called as the central atom or ion. So, here cobalt is the central ion, central metal ion, okay? And you take this nickel tetracarbonyl, here nickel is the central atom, and here another complex. So, here iron is the central ion, central metal ion. This is hexacyanide iron ferrate 2 actually. Okay. So, this is the central atom or ion in the coordination entity. So, usually actually central metal or ion, they act as Lewis acids because they are the electron pair acceptors. Okay. You can get a question on ligands like this. Okay. See, which of the following is a monodentate ligand? He gave 4 options. Oxalate ion, you know, it is a didentate. Ethylene diamine, it is a didentate. EDTA, polydentate, but thiocyanate ion is a monodentate ligand. So, option 4 is the right option. The next important term is ambidentate ligand. What is an ambidentate ligand? In a ligand molecule, if there are 2 different donor atoms, it is called ambidentate ligand. For example, okay, this is a metal, nitro group. In nitro group, both nitrogen and oxygen can form bond, coordinate bond with metal. Okay. If nitrogen is involved, then the name will come as nitrito N. Okay. If oxygen is involved, then the name comes as nitrito O. So, here both nitrogen and oxygen are capable of forming coordinate bonds with metal. Okay. Next, another example, here thiocyanate ion, here sulfur and nitrogen can form bond. If sulfur is involved, it comes as thiocyanato S. Alternatively, if nitrogen is involved in the bond formation, then it comes as thiocyanato N. See, we can get a question on ambidentate ligand like this. Okay. Which of the following is not an ambidentate ligand? So, he gave 4 options. These 3 are ambidentate ligands. Carbon monoxide is not an ambidentate ligand. So, 4th is the right option. Okay. Next, ligand is a very important term. Okay. Ions are molecules that are bound to central atom in coordination entity are called ligands. What actually happens here? You see, examples, there can be ions like cyanide ion, chloride ion or hydroxide ion. They can donate electron pair to the vacant d orbitals of the metal and form coordinate bonds. Okay. So, these can be ions, or they can be molecules like ammonia or water or carbon monoxide. So, they give or they donate electron pair and form a coordinate covalent bond with the metal. Hence, the name they are called, these compounds are called coordination compounds. Okay. You can get a question on coordination number like this. Okay. The you will give a complex and you will ask the coordination number of the central metal ion. Okay. So, here 4 options he gave. Now, we can see here ethylene diamine is a didentate ligand, 2 such molecules are there. So, here 4 plus 2 6. So, the coordination number of cobalt in this complex is 6. The next one, see, the ligand that is bound to a central metal, we call it is unidentate only when one atom of that ligand binds to the metal. Okay. See here, this is the metal, you have ammonia, only nitrogen is bonding to the metal. So, you can see prior to the bonding there is one electron pair, Now that electron pair is donating to the metal and forming a coordinate bond. So once the bond is formed, it is disappearing. Okay. So this is an example. Alternatively, a ligand can be didentate, that is, in only one molecule there will be two donor atoms which can bind to the metal. For example, this is a metal, you can see ethylene diamine, it is also called as ethane 1,2-diamine. Okay. So now these are the two lone pairs of electrons that can be donated to the metal. So it is a didentate, two bonds, one molecule can form two bonds. Okay. Now one more example we can have, this is a metal, this is oxalate ion, here also it can form two bonds. So these are the didentate ligands, that is ethylene diamine and oxalate ion. There is a polydentate ligand I am showing here. This is ethylene diamine tetraacetate. Okay. You can see total 6 atoms that can coordinate, that can form a bond with the metal. Okay. So here you see these are the different electron pairs on the different atoms. Okay. Now here this is an hexadentate ligand having 4 oxygen atoms and 2 nitrogen atoms capable of forming coordinate covalent bond with the metal or metal ion. Okay. Next, see, when a didentate ligand or a polydentate ligand binds to metal, we get a ring complex which is called as the chelate complex. Okay. Now metal, a bidentate ligand, just now I have shown you. Now it is formed a bond. Now we can see a 5-membered ring is formed. Okay. These are the 5 atoms, okay, that are involved in the ring formation. So a didentate and or polydentate, the tridentate, tetradentate, like that, when they form a coordinate bonds with metal, the result is the chelate complex or the ring complex, and such ligands are called chelating ligands. Okay. Next, on this concept we can get a question like this: which of the following complex will give white precipitate with aqueous barium chloride? So here you should have an ionizable sulphate ion. If you observe these complexes, okay, in complex 1, 2 and 3, in all the 3 there is sulphate ion, but in complex 1 and 2 this is inside the square brackets, that is non-ionizable, but in complex 3 it is outside the square brackets, this is ionizable. So therefore third is the right option. Coordination number is a very simple concept. See, it is the number of ligand donor atoms to which the central metal atom or ion are directly bonded in the coordination entity. It is a very simple concept. Look at here. To the metal ion, 6 chloride ions are bonded. Therefore, coordination number 6. Similarly, here to the nickel ion, 4 ammonia molecules are bonded. So, coordination number 4. Here to the cobalt, 3 ethylene diamine molecules are bonded. Each ethylene diamine is a didentate ligand. 3 such molecules are bonded. Therefore, coordination is a bidentate ligand. Therefore, coordination number is 6. In the similar manner, if you take when oxalate ion is the ligand, it is a bidentate ligand, 3 such molecules are bound. Therefore, the coordination number will be 3 into 2, that is 6. Okay. Like this, coordination number you can easily calculate by looking at the formula of the particular complex. Okay. Next, see, in determining the coordination number, you should consider only sigma bond between the ligand and metal, but not the pi bond. Okay. Next, coordination sphere is a very simple one. Briefly we can say the part of the molecule within the square brackets is the coordination sphere. Okay. So here this is the coordination sphere which is actually non-ionizable, okay, and this is the ionizable part of the complex. Okay. See, on coordination polyhedron you can get a question like this. Usually you will get the match the following type of questions on this. Okay. So, one side he has given the different coordinate polyhedron and the other side he has given the examples. Now we need to match them. So, octahedral complex 1B, tetrahedral complex 2C, square planar complex 3A. Okay. So, he will give various options, among which you have to see this as the correct option. Sometimes he will give the match the following, or sometimes he will give directly a complex and he will ask you what is the corresponding polyhedron for this, or he will give the a polyhedron from which you have to identify which complex is actually matching that particular polyhedron which he has given. Okay. Three types of questions he can ask, either match the following, or otherwise he will give the example and you have to find out what is the polyhedron, or he will give the polyhedron, okay, and you have to see which complex is corresponding to that particular polyhedron. Okay. The next important term is coordination polyhedron. Okay. What it is? It is the spatial arrangement of the ligand atoms that are bonded to the central atom or ion defines coordination polyhedron. The different spatial arrangements can be here in the octahedral manner. Okay. So, central metal with 6 ligands, it can be tetrahedral, okay, central metal with 4 ligands, or it can be square planar. Okay. You can see metal with 4 ligands. The others are trigonal bipyramidal, metal 5 ligands, trigonal bipyramidal and square pyramidal. Okay. So, these are the different coordination polyhedron. See, you can get a question on oxidation number like this. He has given 3 complexes and is asking us to find out the oxidation state of central metal atom or ion. First one, here the contribution by cyanide ion, each cyanide ion is -1, -1 into 6 -6, net is -4, therefore, this is +2. In the second complex, the contribution by ammonia is 0 and here -1 into 3 -3, so cobalt is +3. And the nickel complex, carbon monoxide is a neutral ligand, its contribution is 0, so nickel is oxidation state is 0. So, therefore, first is the right option. Okay. You can have a question like this also. Okay. He will give a complex and is asking us to find out coordination number and oxidation state of chromium in this particular complex. So, here you can see oxalate ion didentate -2 into 3, this is -6, potassium +1 into 3 +3, therefore, chromium has to be +3. Okay. So, the oxidation state is here +3 and the coordination number you can see -2 into 3, that is the 2 into 3 didentate ligand, 2 into 3, therefore 6. So, third is the right option for this. Okay. Coordination number is 6, oxidation state is +3. Okay. Next is the very important one, oxidation number of the central atom or ion. Okay. So, what it is actually? It is the charge that central metal carries if all the ligands which are bonded are removed along with the electron pairs. So, that is the oxidation number. So, how are we going to calculate? It is a very simple procedure. Say you want to calculate the oxidation state of cobalt. So, X plus ammonia is a neutral ligand. So, its contribution is 0 is equal to +3. So, oxidation state of cobalt is +3. Another example, here want to calculate the oxidation state of copper, X plus each cyanide ion will contribute 1 negative charge. So, into 4, therefore, -4 is equal to -3. So, X is equal to +1. Therefore, oxidation state of copper is +1. In the similar manner, to calculate the oxidation state of iron, X plus oxalate ion will carry 2 negative charges. So, -2 into 3, -6 is equal to -3. So, X is equal to +3. So, oxidation state of iron is +3. Okay. So, like this we can calculate the oxidation state of the central metal atom or ion. Okay. See, on this concept a question has come in NEET 2024. Okay. The question is, he gave this complex and is saying this is a homoleptic complex. The other complex he gave and is calling this as the heteroleptic complex. This is statement 1. Statement 2, the first complex is homoleptic because it has got only one kind of ligand, and in the second one there are two types of ligands. So, statement 1 is correct, statement 2 is correct, both are correct. Second is the right option. Next, homoleptic complex is a very simple concept. Okay. See here, the central metal is bonded to only one kind of ligand. There is only one ligand or one kind of ligand, that is ammonia. In heteroleptic complex, what is happening here? The central metal is bonded to more than one kind of ligand. So, you have ammonia, you have chloride ion. There can be more than two also. If there is more than one, it is the heteroleptic complex. Okay. Now, one of the most important topics of coordination chemistry is related to the structure and bonding in complex compounds. The first one is the Werner's theory of coordination compounds. It has got certain postulates. First, I will explain the postulates and then I will show with examples. Okay. So, according to this theory, a coordination compound, in coordination compounds, metal will have two types of linkages or valences. What are they? One is the primary valence and other one is the secondary valence. I shall show with examples, just wait. Okay. Primary valence are satisfied by the negative ions that are ionizable, whereas secondary valence are satisfied by the ligands which are non-ionizable and they correspond to the coordination number. Okay. Now, the different ligands which are bonded through secondary linkages, okay, they actually contribute to the spatial arrangement corresponding to the coordination number. Okay. Now, let us understand Werner's theory with suitable examples. Okay. Now, first one, a complex we have taken, a cobalt complex, hexamine cobalt 3 chloride, central metal, 6 ammonia molecules, ligands forming coordinate covalent bond, okay, non-ionizable, they are satisfying the secondary valence. The 3 chloride ions, they are satisfying the primary valency, these are ionizable. Okay. Now, when you add excess AgNO3 to this, you will get 3 moles, okay, you will get 3 moles of AgCl, because there are 3 chloride ions which are ionizable. Therefore, you can get 3 moles of AgCl precipitate when you add excess AgNO3 to 1 mole of this complex. Okay. And the solution conductivity corresponds to 1:3 electrolyte. Actually, when you dissolve this complex in water, totally you will get 4 ions, 1 complex ion and 3 chloride ions. Totally we will get 4 ions when this complex is dissolved in water. Okay. Another complex, pentamine chlorido cobalt 3 chloride, here cobalt metal, central metal, 5 ammonia molecules, 1 chloride ion, they are satisfying the secondary valency, that is why I have shown with the arrow mark. This chloride ion is also satisfying the primary valency, okay, and the remaining 2 chloride ions, they are satisfying only primary valency which are ionizable. Therefore, when we add excess AgNO3, only 2 moles of AgCl is precipitated, and here the solution conductivity corresponds to 1:2 electrolyte, because this on dissolution in water 1 complex ion, 2 chloride ions are formed. Okay. This is like this for the second complex. Now, third complex, tetramine dichlorido cobalt 3 chloride, it is a green colored complex. We have another isomer, violet colored complex is also there. Okay. Now, cobalt, here 4 ammonia molecules and 2 chloride ions satisfying the secondary valence, okay, and they are also satisfying the primary valence. These 2 chloride ions are also satisfying the primary valence, okay, and 1 chloride ion exclusively only the primary valence. This is ionizable. Therefore, it gives only 1 mole of AgCl precipitate when you add excess AgNO3, and the solution conductivity corresponds to 1:1 electrolyte, because this complex when dissolved in water we will get two ions, one is a complex ion, the other one is the chloride ion. Okay. See, on the Werner's coordination theory complex, you can get questions like this. Primary and secondary valency of platinum he is asking in a complex. So, here the chloride ions will satisfy the primary valency, and ethylene diamine and chloride ions both put together will satisfy the secondary valency. So, here 2, this is a bidentate ligand. So, total 4 plus 2, 6 is the secondary valency and 2 is the primary valency. So, option 4 is the right option for this. Sometimes in the same complex he can ask the question like this: number of ionizable chloride ions present in this complex. Actually, there are no ionizable chloride ions, because whatever the chloride ions that are present, they are within the square brackets, these are non-ionizable. Okay. The next one, you can also have a question like this: which of the following will have maximum ionic conductivity? So, if complex 1 dissolves in water, here you will get 1 ion plus 4 ions, total 5 ions will get. Here this is 1 ion plus 3, 4 ions. Okay. Here 1 plus 2, 3 ions, and it is a compound, it is a molecule. Okay. So, here the maximum conductivity will be exhibited by, that is complex 1. Okay.